And I'm asking a question. The first question I'm asking you, and I'm going to give you a couple minutes, is to calculate in watts the duty of this heat exchanger, right? And it's here in Socrates. It's for the same problem. You have everything you need here, and I'd like to give you, say, 2 minutes to do this. You would know what formula to use. So how do we go about this? I think pretty much everybody got it right, but we said the equation of duty is the one we have here. So we have Q equals, what do you use, hot or cold, to calculate duty? Okay, either. Do you want to use cold? How do you do it? If you don't have the temperature, how do you know if it gains or loses heat? Right? So in theory, it should be the same, but in practice, they say, hey, I have this hot oil, I want to cool it to this temperature. My cooling fluid is this. I have no idea what temperature the cooling fluid is coming out. So right now, we are stuck with using the hot one. And this is 0.1. You know, you have it in your notes. I don't need to redo everything, but the actual number is 8524 watts, as most of you said. Right? Okay, cool. Awesome. So I'm going to go to this part of the board. You already have the next question there. And the next question is, all right, fine. What is the outlet temperature of the cold fluid? If you know that this heat in is the same as the heat out, now we go to the cold fluid. We know the flow rate. We know the specific heat, right? We know what temperature is coming in. We solve for TCO, and that is when we solve it, we have that would be 40.2 degrees C. Now this is quite awesome, because a heat exchanger is a serious thing, very expensive, very essential for companies. And little by little, we're chipping away, and we're calculating things that by no means anybody could calculate just out of intuition. Okay, question number 3. The question number 3 is, what is the delta T log mean? So in this case, we would have the delta T2 is 59.8. Delta T1 is 30 degrees. Let's put the C's here. Over the log of 59.8. Right, and this is going to give us 43.2 degrees C. Right? Cool. All right. The next question. So you see, all these equations are relatively simple. Very powerful stuff. Very powerful stuff. Next question is, what is the overall heat transfer coefficient? As we do this, let me give you a pointer, right? That is going to be useful to you. Here we have the formula from where we would calculate overall heat transfer coefficient, right? Now, this formula requires you to know lots of things, but there is not even room to write all the things you need to know there. Let's go one step at a time. Does the problem statement say anything about fouling? Okay, if nobody tells you about fouling, I suggest you say, okay, I claim there is no fouling. If somebody tells you about fouling, you better do it with fouling, right? But so now we went from 5 terms to 3 terms. Now, we have to calculate heat exchange by conduction, right? In the pipe. What do you need to know to calculate that heat exchange? Other than the equation, what do you need to know? For example, how thick the pipe is? I think, right? Whether it's inner and outer diameter or thickness or something. Do you have that thickness in the problem statement?
Yes.
Okay.
The inner and the outer diameter.
Oh, okay. You bring an important point. So we have an inner and outer diameter. But let's look at what. The inner diameter is the inner diameter of the annular conduction section for the, let's see. Super important. So I'm glad we're discussing this. Look at this. You say inner diameter and outer diameter, right? But this is oil in here. That's not resistance to conduction. Oh, right? I didn't mean to be tricky. That's a book, right? So when I meant resistance to conduction, it was inner and outer diameter of this pipe. This black line here essentially is the wall of a pipe. But they don't give us that. If they don't give it to you, what you assume is what you like, and is what it should be also, that resistance to conduction is negligible, so that the pipe is thin enough that it doesn't matter from the point of view of your calculation of overall heat transfer coefficient. So for this problem in which they gave you no information, we're going to say, you know what? Whatever that is negligible. If on the final we say the inner and outer diameter of the pipe, you better calculate it or make an argument better than just a guess about why you should neglect it. If we do that, now other things. This is not a finned pipe. So this is going to be this efficiency. This is 1. This here is going to be 1. Things are getting quite simple. Now here we have area of reference, area of cold fluid, and area of hot fluid. What can you tell me about those? Yeah, of course they are the same. And the reason is this can be whatever you want. So let's discuss this last. But the area of heat exchange for the cold fluid and the hot fluid is essentially the same because we have assumed the pipe is a thin wall, right? And if the wall is so thin, inside area and outside area of this cylinder is the same, right? So these two guys would be the same. Now, if I can choose any reference area I like, I'm going to choose that one, right? So now all these guys go away, right? This is true because we're saying it's a thin wall pipe. And we say it's a thin wall pipe because they didn't tell us anything else. Right? But in any case, when you design a heat exchanger, what you don't want is to be creating your own worst enemy that is thermal resistance. So you design it with as thin a pipe, a wall as you can. Now, you have everything you need to calculate this overall heat transfer coefficient. Question to you. Is there a dominant resistance? Okay, which one? So it will be the resistivity of cold, the convection coefficient of cold was 2250 watt per meter square Kelvin, and of hot was 38.8 watt per meter square Kelvin. Yes, the hot fluid is the dominant resistance, right? Because in a series resistance, series circuit, the highest resistance dominates. So, for example, if I put fins on my cold fluid, what do I gain? Nothing. And this, just pay attention to me for a brief second, because this issue of dominant, it matters so much. In industry, you have all the time people who say, well, how can we make this heat exchanger better? And they would say, oh, well, the book says put fins. And fins in water is good because it's not going to get fouled. There's many good reasons to put fins. But then you go there, and you say, okay, if I put fins and all of a sudden my heat transfer coefficient in water is double, right? My convection coefficient is double. Does it buy you much? It doesn't buy you anything. This is the one you have to attack, right? So these pieces of insight are so much more important than the plug and chug calculations, because just by looking at this, you realize, worry not about the water. If we do anything, let's do something about the oil. Yeah?
So, like fouling, you have to account for what makes.
Oh, you can put fins in your oil if you want. Now, that's a design question for which I don't have the straight answers, but I can tell you some things I heard about. Fouling is a very foul thing, right? And so it's when you clean them, right? If you have fins, it's very difficult. So you would seldom want to put fins on the oil side, right? So, but you can do things. You can try to induce turbulence. These calculations, when you go to the book and you see, both are internal flow calculations. And they're quite difficult. You have to check for the Reynolds number to see if it is turbulent or not, right? So what you're going to see is that this is turbulent and this is laminar. So maybe you can try to make this one turbulent, right? Things like those. Let's calculate the length of this heat exchanger. How long should it be? Let's see how we calculated the length, right? And sometimes they might ask you, how many tubes should we have, right? And it all comes from this design equation. The design equation that is this one, in reality, is kind of written wrong, because what you want to know is area. You know Q and delta T from something else. So area is Q over U delta T, right? And which is Q over U F delta T log mean, right? And if we say then length is area is pi diameter length, and so we would have length is area over pi di, and an area we had calculated it here, so we would have Q over U F delta T log min pi di. What is F in this heat exchanger? It's 1 because it's a counterflow heat exchanger. If we have a heat exchanger in which we have one shell, 2 passes, you need to go to those tables I showed you. But this case is simple. So this is 1, and then the length we got, some of you didn't believe it, is essentially 65.9 meters. So super long. These concentric heat exchangers, they're horrible. Don't buy them, right? What you want in this case is a lot of tubes, right? Instead of having like 65 meters, 66 meters of heat exchanger. If you were to have 2 tubes, you would have half that. If you were to have 4 tubes, half of half, right? So that's why you have so many tubes in a heat exchanger. Just the concentric would take forever.